Good morning, everyone. It's very exciting to be here, to see so many new faces, so much excitement. So today, I'm going to share with you some of the plans we have at Berkeley following the AMPLab. So let me say a few words first about the AMPLab. So the AMPLab is a research project at Berkeley, started in 2011, and is going to end up this year. The mission of the AMPLab was to make sense of the big data using a holistic approach involving algorithms, machines, that is systems, and people, that is crowdsourcing. The AMPLab was founded both by the government agencies, like NSF and DARPA, and by over 30 companies over its 6 years of existence, including Amazon, Google, IBM, and SAP. The goal of the AMPLab was to build the next generation of the open source data analytics stack to be used across industry and academia. So it's again, why is this relevant to you? It's because, like Andy mentioned, AMPLab was the home of the Apache Spark, which all of us are using today. In addition, it was home to other systems you may have heard of or you may have used, like Mesos and Alusio, formerly known as Tachyon. So of course, the obvious question, now that AMPLab is coming to an end, is what is next? So I'm very excited to announce that we are going to have a next lab at Berkeley, which will be called RISELab, and RISE stands for Real-Time Intelligent Secure Execution. To put things into context, if the focus of the AMPLab was primarily on interactive advanced analytics on batch data, mostly, the focus of the RISELab will be on real-time decisions on live data. So why this focus? Well, today you hear more and more that the holy grail of turning the data into value is making decisions and taking actions on the data. So from here, the agenda of the RISELab follows quite naturally. Indeed, in general, faster decisions are better than slower decisions. Decisions on fresh data are in general better than decisions on stale data. And decision on personalized data is better than decision on generic data. As such, the goal of the RISELab is to support real-time decisions on live data with strong security. By real-time here, we mean the ability to make decisions in milliseconds. By making real-time decision on live data, we mean that we want to make these decisions on the current state of the environment, not on some state which is 1 day old or several hours old. And by strong security, here we mean to provide privacy, confidentiality, and integrity. Now, if you build a service and your service provides privacy and confidentiality, then it's a much higher chance for your customer or users to share their information with you, which will allow you to make better decisions. Regarding the integrity, now more and more of these applications are deployed in the cloud. So if you are going to deploy your mission-critical application or service in the cloud, data integrity and computation integrity are very important properties. So here is basically how a decision system looks like, broadly speaking. You have some data coming in. The data can be user logs, machine logs, pictures, videos, and so forth. And this decision system, like the name implies, will make some decisions for users or for some devices. Many of these systems also provide a feedback loop, so they use the outcome of the previous decisions to improve the future decisions. And if you look inside this box, there are 2 stages, basically. The first stage takes this raw data and pre-process it and create some intermediate data. A classic example is it's a training. Basically, you train on the raw data and you create a model. And then in the second stage, you can have either a user querying this intermediate data and making decision based on the answers to her queries, or you can have an automatic decision engine. And if you look at this pipeline end to end, there are two performance metrics which are important. The first is the update latency. And this is how long it takes to update the model when the input data changes. And this is related with the freshness of the data in which you are making the decision. The second one is the decision latency, as the name implies, is the time it takes to make the decisions based on the intermediate data. And of course, ideally, you want both low update latency and low decision latency. Now, it turns out this is pretty hard. So why is hard? Because we have a lot of demands. So first, we want high-quality decision. And this has a bunch of subdimension here. First, we want the decision with sophisticated decision. This is not simple aggregate or a simple SQL query. Think about fraud detection. Think about forecast. Think about coordinating a fleet of drones in real time. These are pretty complex decisions. Then we want the decision to be accurate with low false positives and negatives. But more importantly, we want the decision to be robust. Robust to noisy inputs and robust to unforeseen data. Okay? Especially when you are talking about real-time decisions, humans are not in the loop. And I want to spend a little bit of time on this unforeseen data. So the problem here is that what happens if you see an input which you've never seen before, right? First of all, you need to recognize that, and then maybe to take some kind of conservative decisions. And this is not easy. Today, for instance, it's very easy to train a neural network to differentiate and classify correctly pictures which contain dogs versus picture which contains cats, right? You train them, and they are going to be pretty good at that. But what if you show a picture containing an elephant? Okay? Many of these systems will classify maybe as a dog. So you want actually what you want is that their classifier to say, I've never seen this before. Okay? And eventually make some default conservative decision. We also want low latency, like I mentioned, for both updates and decisions. And we want strong security. Now, I want to tie this in together by giving you an example. So the example here is aiming to solve the zero-time defense problem. So here you have an attack, and as you know, today a virus or a worm can infect millions of machines in seconds. So how would an ideal solution look here? Well, an ideal solution here will be a solution which monitors the traffic at hosts, servers, routers in the internet, and it is doing this monitoring in real time and try to infer when an attack occurs. Okay? And then, when it detects an attack, you want to patch, you want to patch software in real time, you want to install new rules for the firewalls, so therefore to dwarf the attack. So it should be clear here that, again, the decision is pretty sophisticated. Every attack is slightly different. Here we assume that for the previous attacks, you already have the right patches, you already have the right rules in your firewalls. But for the new attack, it will be slightly different. So you need to learn that. And you need to learn that in seconds. Now, the accuracy and robustness they are also very important. On one hand, you don't want to miss an attack. On the other hand, you don't want to misclassify some legitimate traffic as being an attack, right? Because then you are going to deny the service to a legitimate application. And then you want to make these decisions once you identify an attack really in milliseconds. Security also is very important here, because if this kind of service doesn't ensure privacy, then it's very unlikely for the customer of users to let this service monitor their traffic. Now, there are many other applications sharing the same pattern, whether it's a parking assistant, IoT applications, earthquake warning, manufacturing pipelines, fleet driving, virtual companion, and so forth. And this, I put on this slide the properties for this application. So the only one I want to mention here is that if you look at the latency for the update and the decisions, the lower bounds there are seconds on updates and milliseconds on decisions. Again, the update here refers of how long it takes to incorporate the new data in your intermediate data in your model, and is related with how fresh is the data on which you are going to make decisions, and millisecond, how long it takes to make actually decision. Now, building this application today is actually very hard. First, automated decisions on live data are hard, and if you are talking about removing the human from the loop, they are even harder because of the robustness requirements. Security is pretty poor. Exploits are daily occurrences. And even if we do this, because we do something like this today, if you think about ad bidding, if you think about fraud detection and things like that, when we do that, we build a system, a separate system for these applications. And building a separate system is expensive, takes a lot of time. So in the RISELab, we want to address all these challenges. First of all, we want to provide support for real-time, sophisticated decisions that guarantee worst-case behavior on noisy data and unforeseen inputs. We want to ensure privacy and integrity without impacting the functionality and possibly the performance. And finally, and probably the most important, we want to build a general platform. We call it Secure Real-Time Decision Stack, which will make it dramatically easier for people to build this kind of applications which require to perform real-time decisions on live data. Now, these challenges open a lot of exciting directions, research directions, at least in 3 areas. On the system side, we are looking at systems which can provide 100 times lower latency and 3 orders of magnitude higher concurrencies than today's Spark. Whether this will be Spark 3.0 or maybe another system remains to be seen. But what this will allow us is to perform tens or hundreds of thousands of decisions per second, so you support kind of users and devices everywhere in milliseconds with decision. On the machine learning side, we are looking at online machine learning algorithms which are robust. And finally, on security, we are looking to achieve all these properties without impacting performance or functionality. So in the second part of the talk, I'm going to switch the gears, and I'm going to tell you about 2 early projects which are relevant both for this community and for the RISELab, and present some very early results. The first project is called Drizzle, and it's in the area of streaming. And when it comes to streaming, all of you know by now that there are 2 kinds of systems, micro-batching and record at a time. An example of micro-batching system is Spark. And the advantages of these systems is that they inherit the desirable properties which come from the batch systems, like fault tolerance, straggler mitigation, various optimizations, and also the unification with other computation models like machine learning and graph processing, like you've seen before. In contrast, record-at-a-time systems like Storm and Flink, they don't necessarily have all these properties, but typically provide lower latency. To this point, Yahoo, several months ago, did a benchmark in which it compared these 3 systems, Storm, Flink, and Spark streaming. And for that, the input was 20 million JSON ad events per second. They belong to 100 campaigns. And what they want to do here is over 10 seconds windows to compute the counters, the number of ads for each campaign. Okay? The latency here is a time when, from when the window ends until when all the data is processed for that window, when you have the results for that window. And the SLA for that latency is 1 second. And probably some of you know about this study. And maybe you are not surprised here that Storm and Flink, the record-at-a-time systems, provide indeed lower latencies than Spark. So in this research in Drizzle, We set that as our challenge to show that actually there is nothing fundamental about micro batching systems which precludes them to provide low latency. In particular, our goal was to get to a latency which is 1 order of magnitude better than Spark. But before then, let me spend a little bit of time, so why, in this case, the Spark was slower. And you may not be surprised, you already know that, because Spark is doing quite a bit of heavy lifting when it's processing every micro batch. In particular, the master schedules tasks for each worker. The worker deserializes the task, executes the task, and processes one micro batch. After that, the workers send the status about resource availability to the master, and the master proceeds with the next step to process the next micro batch, which again involves sending the task, processing the next micro batch, and then sending back the cluster status information to the master. Okay? Like I mentioned with Drizzle, our goal was to reduce the Spark streaming latency by at least 1 order of magnitude. And from the previous example, there is one key observation which allows you to do that. And the key observation, if you look at the consecutive iterations, when you process every micro batch, actually the processing is very similar. The tasks are basically the same. The dependency between the tasks are the same. What is different is the inputs. So using this observation, what we are trying to do is to remove the master from the critical path and push the scheduling decision to the workers. Actually, the idea is quite simple. Instead of the master sending one set of tasks for each micro batch to process to the workers, it will send a group of tasks. And this group contains tasks which are going to process multiple micro batches. So right now, the master sends a group of tasks to each of the workers, and then the workers, they are going to process a succession of micro batches without the master involvement based on the tasks which are in the group. Okay? Of course, from time to time, the workers will send the cluster status information back to the master so the master can adapt when there are failures where there are changes in the workload. So how well does it work? So this was the original kind of results, Spark versus Flink. This is a cumulative distribution function for latency. And of course, if you are at the left, you are better. So, quite a bit of difference. But now here is how Drizzle performs. Sorry. So as you can see, Drizzle has pretty similar latencies with a record-at-a-time system, in this case, Flink. By the way, Storm performs very similarly, so I'm not showing it here. So this is pretty good. So now we have, at least for this example, a micro-batch streaming system performs pretty similarly with a record-at-a-time system. But actually, things are better. And they are better because, remember, with the micro-batch streaming systems, we can use the same kind of optimization we use in a batch system. And this can buy you performance. So here it's one particular simple optimization, which we use a reduce by on the map side. So basically what we do here, for every micro batch, we are going to compute the partial counters for each campaign and then aggregate. By doing so, the amount of data we shuffle is reduced considerably, and therefore the end-to-end latency to process and all the counters is dramatically reduced. So in this particular case, you can see that Drizzle performs in terms of latency approximately, roughly, almost 3 times better. But what is more interesting here is that even Spark for this particular benchmark with this optimization performs better for the same reasons. We couldn't do the same optimizations in Flink because the Flink is actually partitioning the data before applying the window operators. this is fundamental, because if you have microbatches, you can apply and you optimize for the data within microbatch. If you compute and if you on one record at a time, you have much less opportunity for this kind of optimizations. Now, another example in which you can see the advantage of the microbatch systems is fault tolerance. Here again, we are using the same kind of techniques like and reusing from the batch systems. So in this figure, it's another experiment. We have 128 nodes. On the y-axis, we have the latency. Notice that it's a log scale. And on the x-axis is the time. At time 240 seconds, we fail one node. And as you can see, the behavior of all the system is pretty similar. You have a bump in the latency, and then the latency gradually converges to the latency before the failure. So you have this kind of recovering time during which the latency is high. However, if you look at the magnitude of the numbers, you can see here that actually, if you look at a record at a time system like Flink, you are going to have latency of over 100 seconds. Remember, the SLA here is only 1 second. Also, the recovery time, it's like almost 50 seconds. Okay? In contrast, for Spark and Drizzle, the increase is much smaller, and the recovery is shorter. In particular, Drizzle recovers 5 times faster, and the latency is 10 times lower, the maximum latency. So why is that? Now, all these systems, they use checkpointing. However, the difference is the following. In the case of record-at-a-time systems, you have to go all the way to the checkpoint and recompute everything. In contrast, Spark and Drizzle, they use a lineage. They leverage a lineage. So therefore, they don't need to recompute the partial results since the last checkpoint, which are already in the system. The only thing they need to recompute is the partial results which are on the machine which failed. And by the way, this recovery can be done in parallel. Now, one question I'm always asked when I'm talking about failures in the case of streaming, does this matter? Okay? And to drive home the point here, a 4.9 SLA, which is not unheard of, means that you cannot exceed the SLA in a single day by 8.6 seconds. Now compare that of how long it takes to recover for a record-at-a-time system, which in this case is 50 seconds. Okay? So that time is quite significant. So finally, I'm going to talk about the second project, which is called Opaque. And this is in the domain of security. Now, the state-of-the-art security today is what? In the big data systems. Perform authentication, encryption at rest, encryption in motion. And you say you are pretty much done. And that can be true if you use Spark in isolation. But Spark is not used in isolation. Actually, Spark runs on an operating system, which runs maybe on a hypervisor, use a cluster manager, and everything runs on a private or public cluster. Okay? So this means that just encryption at rest in motion is not enough. Because, for instance, it doesn't protect you against the OS or the hypervisor being compromised. And if these are compromised, the attacker can get root access and can see the encrypted data in memory, can have access to the keys, and all of this stuff. There are actually more subtle attacks. And there are these attacks which exploit the leakage from the pattern, access pattern. So it turns out that if you look at the size of the results, as the pattern of the shuffle, as the pattern of the access of the data in memory, and on the SSDs or on disk, you can get a lot of sensitive information. So the goal of Opaque is to protect against this kind of attacks. And to do so, we leverage the latest developments in the hardware encryption, in particular Intel XGX, which provide you this hardware enclave construct. What a hardware enclave is what enables you to do is to run a software in this hardware enclave, and this software is going to be protected by the hardware. This means that it doesn't matter whether the other operating system on the same machine is going to be compromised. Your software running in the enclave is protected. And to this end, we're implementing secure distributed relational algebra for Spark SQL on top of the Catalyst, the query optimizer in Apache Spark. There are two modes to run Opaque. In an encryption mode, and this protects you against compromised software, like when the OS is compromised. And in oblivious mode, which in addition provides you protection against leakages from the data access patterns, So how does it perform? Well, here are some very preliminary results. Here we have 3 queries for the big data benchmark. On the y-axis, you have the runtime. Again, you see the log scale on the y-axis. And there are 2 points to note here. First, with orange, Opaque in the encryption mode performs very similarly with Spark SQL, which is unprotected. Okay? Actually, in some cases, like query 1 and query 3, it performs better, which is counterintuitive. So why is that? Well, that is because Intel SGX provided a toolkit in C++. So therefore, we had to re-implement these operators in C++. So that gives us an advantage. On the other hand, the Opaque in oblivious mode is more expensive. It can be 100 times more expensive to run a query in the Opaque or oblivious mode than the original Spark SQL. Okay, so that's quite a bit. However, if we put things into perspective, this is 3 orders of magnitude, actually it's over 3 orders of magnitude better than state-of-the-art oblivious algorithms, other oblivious algorithms. Okay? And if you have super sensitive data, it's actually for some queries, even today, 100x could be at the borderline of being practical. But of course, this is just the beginning. So to summarize, we are very excited that at Berkeley to start this new lab, RISELab, and the goal of the lab is to develop a secure real-time decision stack, which is an open source platform, tools, and algorithms for real-time decision on live data with strong security. We got a bunch of promising results already, and of course, we are hoping for much more over the next 5 years. And more than anything, we hope to share these results and with the community. Thank you.